So, um, imagine for a second that you need to render perfectly distributed 3D geometry. Calculating sines, cosines, square roots, all of that. But you have to do it without a single logic gate dedicated to multiplication, like zero. No math libraries, no massive memory banks, no floating point units, just raw wire soldered in reverse and a few really ingenious mathematical tricks.
Right, which is just wild to think about today. I mean, we have been completely conditioned to throw just gigabytes of memory and endless clock cycles at these kinds of geometric problems.
Yes, totally.
Like, if we want a perfect sphere, we just spin up a massive GPU and brute force billions of calculations. In software, we basically have the luxury of infinite space, so we just use it.
Exactly. And that brutal restriction, the complete absence of infinite space, is exactly what we're getting into today. So welcome to the Deep Dive. Today's source material is this highly technical, honestly fascinating slide deck by a developer who goes by the handle at Lux036. It's titled Silicon Geometry, Quartic and Low Discrepancy Hardware Architecture.
It's a great deck.
It really is. And the mission for our deep dive today is to take you on a journey from high-level abstract math down to the literal physical metal and wires of hardware. Even if you aren't a hardware engineer, you're going to appreciate this. We're exploring how to physically hardwire spatial uniformity right into silicon.
Yeah, because the developer's approach here is just a masterclass in extreme problem solving. When you drop down to bare metal silicon design, every single logical operation and every stored digit physically takes up space on the chip.
Right, you're paying for it in physical real estate.
Exactly. You have to treat logic gates like precious, expensive real estate. You can't just import a math library.
So let's start with the foundation of the architecture here, which is generating points that are perfectly evenly spaced out. Now, random sampling is usually the obvious first thought, but it has a fatal flaw when you're trying to fill a space. It clumps.
Oh, yeah, it clumps terrible.
Like, think about planting trees in a massive field, right? If you just scatter seeds randomly, some trees are going to grow practically on top of each other and, fight for sunlight, while entirely separate acres of the field are left completely bare.
Right. And to avoid those clumps, mathematicians use what are called low discrepancy sequences. And in this deck, the developer implements the van der Korpet sequence.
The van der Korpet sequence.
Yeah, which basically behaves like an incredibly meticulous gardener. So instead of just tossing seeds, it places the first tree perfectly in the middle of the field. Then it halves the remaining empty spaces and places trees there. Then it halves those spaces again, and so on.
So it guarantees optimal distance between every single point.
Exactly. It fills a one-dimensional space perfectly evenly.
But wait, how does a computer actually calculate this without complex division? Because usually, calculating a van der Korpet sequence means you take an integer, write it out in a specific base, and then reflect the digits around a decimal point.
Right. Which in software involves division, remainders, arrays, all things that are easy in Python, but a nightmare in Silicon.
Hardware division is huge and slow.
Exactly. But the hardware translation for a base 2 van der Korpet sequence, it avoids computation entirely. The cost is literally 0 logic gates.
0. Wait, really? How?
The implementation is stunningly literal. So since the sequence requires reversing the bits of an integer, the developer didn't write an algorithm to calculate a reversal. They just routed the physical wires backwards.
Oh, wow. You just crossed the wires.
Yeah. The wire carrying the highest order bit of the counter is just physically soldered to the lowest order output pin. The math is executed purely through the routing.
That is amazing. So it just requires, 17D flip-flops?
Yep. 16 of them maintain the running counter, and 1 serves as the valid flag. The entire base 2 module takes up a grand total of 72 logic cells. I mean, it's functionally microscopic.
It's basically nothing. But I want to push back on this a little bit because base 2 is easy, right? It's binary. The slide deck highlights the need for odd bases, like base 3 and base 7, to handle more complex composite geometries.
Right.
A hardware chip natively operates in binary. You can't just cross the wires backward to get a base 3 reversal. Natively converting an integer to base 3 usually demands, modular arithmetic and continuous hardware division.
And like we said, hardware division is the absolute enemy of efficiency here. It eats up massive amounts of physical space. So the developer circumvents this using this really clever 2 to the power of n-1 trick.
The bit chunk summation thing.
Exactly. Rather than putting a physical divider on the chip, they fake the division using magic constants.
Okay, let's unpack that trick. So for base 3, the deck specifies a magic hexadecimal constant of 0x0000000AAB.
Right, which in decimal is 43,691. So the hardware takes the incoming value, multiplies it by the specific constant, and then performs a bit shift by 17.
A bit shift.
Yeah. Mathematically, a right bit shift of 17 is identical to dividing by 2 to the power of 17, which is 131,072. And if you divide 43,691 by 131,072, you get exactly 0.333.
Oh man, so you literally just built a divide by 3 machine using only a single multiplication and a wire shift.
Yep. And the bit shift requires 0 logic gates. You're just offsetting the wire connections by 17 positions.
That's brilliant. So by using 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 4925 for base 7, the architecture can just calculate these perfect odd base sequences on the fly.
And the storage efficiency you get from this is massive, because if you tried to bypass the division by simply pre-computing all 64,000 sequence entries and stuffing them into a ROM, the deck notes it would cost 128 kilobytes of physical on-chip memory.
Which, I mean, in software, 128 kilobytes is just a tiny text file.
Right, but on bare metal, 128 kilobytes of dedicated ROM is a huge, expensive physical footprint.
So what do they do instead?
Instead of a full ROM, the design only stores the integer low discrepancy sequence factors, the ILDS factors. The hardware literally just stores 10 exact powers of the base. Those 10 values take up exactly 160 bits.
160 bits. So instead of 128 kilobytes, we're down to 160 bits. That's 6,400 times smaller.
Exactly. It's wild.
Okay, so we have this hyper-efficient engine spitting out these perfectly spaced numbers. But how do we bend them into circles and spheres without hardware multipliers? Because they take up too much physical space on a chip, right?
Right. Generating a circle means you need sines and cosines. And usually that means importing a hefty math library that relies on floating point hardware multipliers.
We don't have space for it.
Exactly. So the slide deck solves this by using CORDIC, the coordinate rotation digital computer algorithm. It calculates complex trigonometry using exclusively shift and add operations. No multipliers at all.
Okay, for anyone trying to wrap their head around this, an analogy, it's like giving someone directions in a city on a grid. Instead of calculating the exact diagonal hypotenuse to their destination, you just tell them to walk a certain number of blocks left and a certain number up. You reach the exact same point using only straight lines, shifts, and adds.
That's a perfect way to visualize it. CORDIC basically rotates a vector step by step using these pre-calculated arctangent values. It adds or subtracts progressively halved angles depending on if it's above or below the target heading.
And in binary hardware, having a value is just shifting the bits one wire over, right?
Exactly. It's the cheapest operation in existence. So there are 2 modes used in this architecture. First is circular mode, which handles the sines and cosines. But there's a catch. As you take those iterative zigzag steps to approximate a smooth curve, the actual length of your vector grows. It stretches out.
Right, because you're zigzagging.
Yeah. It grows by a constant gain factor, which here is 1.647. So the vector stretches by about 64.7% by the end. The fix is just to pre-scale your input by the inverse of 1.647. Then the algorithm runs, the vector stretches naturally, and you arrive perfectly at a scale of 1.
Okay, that's circular mode. But then there's hyperbolic mode, which is used for calculating square roots. And it operates in vectoring mode with a different gain of 0.828.
Oh.
But wait, if we are just plotting points on a flat 2D disk, why do we even need square root calculation?
Oh, that's a great question.
Like if I just take the uniform outputs from the van der Korput module and map them directly as angles and radiuses, wouldn't the points just crowd together in the center like a giant bullseye?
Yes, exactly, because the area of a circle grows with the square of its radius. If you distribute radius values linearly, the center gets insanely dense and the edges get really sparse. So applying a square root transform perfectly counteracts that, keeping the distribution uniform across the whole disk. Ah, okay. And the critical step for calculating that square root in hyperbolic CORDIC is input normalization, right? Because CORDIC only works if the starting number is in a specific range.
Right, it has a limited convergence domain. So before feeding the value in, the hardware checks if it's too small. If the input is less than 0.25, the architecture basically multiplies it by 4 iteratively until it hits the threshold.
And then what?
Well, after CORDIC finishes the square root, it compensates by dividing the result by 2 for every time it multiplied by 4 earlier.
And again, multiplying by 4 is just shifting wires left by 2 positions. Dividing by 2 is shifting right by 1 position. So this whole normalization thing is completely free in hardware.
It literally costs nothing. And get this, there are 0 lookup tables anywhere in the logic engine. It only needs 16 arctangent constants, which takes up a tiny 256 bits of storage.
Wow.
Furthermore, both the circular mode and the hyperbolic mode use the exact same hardware structure. You just flip a control switch, feed it a different set of constants, and the same block of silicon goes from being a trigonometry engine to a square root engine. That is just brilliant hardware sharing. So how do these pieces actually snap together?
Well, the developer uses 5 base modules to create 5 composite modules. So, wiring the Vandercorput sequence directly into the circular Cordic gives you a circle.
And then route that output through the hyperbolic square root module, and you get a uniform disk.
Exactly. Combine all of them and you generate a perfect 3D sphere. And the synthesis results are crazy. The base 2 module takes only 72 cells. The base 3 composite takes 1,443 cells.
Which, I mean, is 20 times more than base 2, but it's still practically nothing for rendering complex 3D geometry.
Oh, it's profoundly small compared to a traditional floating point unit.
Okay, so all of this theoretical hardware math sounds perfect, but the author also shared these 6 specific bug stories in the deck, and honestly, they show just how brutal hardware design actually is.
Yeah, Verilog is unforgiving. In software, a bad variable might crash a localized function. In Verilog, you are designing the physical laws of the circuit. A mistake means you wired the universe together incorrectly.
Let's dive into some of those specific bugs to really show the strict rules of Verilog. Bug 1 and Bug 2 were basically bit-level disasters. Bug 1 was literally just a missing reg signed declaration.
Right. So during the Cordic iterations, the tracking values swing negative. And in binary, a negative number has a 1 in the far left position, the most significant bit.
Okay.
As Cordic shifts to the right, it has to maintain that negative status. An arithmetic shift pulls in new 1s to fill the empty slot on the left. That's called sign extension.
But because they missed that one signed declaration, the hardware defaulted to a logical shift.
Right.
So it pulled in a 0 instead of a 1.
Exactly. And the moment that 0 hit the wire, a negative tracking value instantly transformed into a massive positive number. The geometry was just completely corrupted.
And then bug 2 was a quadrant truncation error. The system used a 16-bit angle representation, so 90 degrees was 0 by 4,000. That requires exactly 15 bits, so the crucial 1 is at the 15th position.
Yep. And during a step to reduce the angle, the variable was mistakenly truncated to 14 bits.
Oh, no.
Yeah, the hardware physically severed the wire carrying the 15th bit. The leading 1 munt dropped off into the abyss, leaving 14 zeros. The value of 90 degrees just instantaneously collapsed to absolute 0.
That is brutal. But my favorite was bug 3, the whole Python versus Verilog thing. This is about the conceptual difference in how they handle time, right?
Oh, definitely. We're taught to program sequentially. In Python, time is a sequence of discrete events. You update X on line 1, and by line 2, Y naturally incorporates the new X.
Right.
But hardware relies on a clock signal. When the clock edge ticks, electricity flows through all physical gates simultaneously. It's strictly parallel. And the Cordic algorithm mathematically requires that the new X and Y be calculated using the original unupdated values of both.
It's like translating an algorithm from Python to hardware isn't just learning a new language.
Yeah.
It's literally like moving to a universe with different laws of physics, where
Yeah.
time happens all at once instead of in a sequence.
That's exactly what it is.
Yeah.
If you use a sequential mindset in hardware design, the math just cannibalizes itself.
And then bug 4 and bug 5 prove that size matters. Squaring a 16-bit number like negative 16,384 gives you over 268 million. That requires at least 29 bits.
But the default in Verilog multiplication makes the output match the widest input, so it tried to stuff a 29-bit result into a 16-bit physical box. The top 13 bits just got lopped off, leaving only zeros, so it output exactly 0, 0, 0, 0, 0, 0. You have to manually widen your registers before the electricity hits.
And bug 5 was just a simple typo write, a missing F and a hex saturation threshold.
Yeah, a missing F. It was supposed to cap at 67 million, but instead, a value of 805 million blew past the typoed threshold and triggered a fallback cap of 65,535. One keystroke bottlenecked the whole engine.
Wow. But bringing it all together, why should you, the listener, care about this hyper niche hardware design?
Because we live in an era of software bloat, we throw massive energy-hungry processors at every problem. This source material is a beautiful reminder of optimization. It proves that with a deep understanding of math and physical architecture, you can achieve perfect results with next to nothing.
Right? The maximum error was less than 0.04% across 88 passing tests, and the z-axis measurements were completely mathematically exact.
Exactly. Human ingenuity scaling down into the atomic layout of silicon will always outclass sheer brute force.
It really leaves you with something to ponder. If a developer can generate complex 3D geometry using zero-gate wiring tricks and simple shift and add logic instead of massive processors, what other complex problems in our modern world are we currently brute forcing with AI and giant data centers?
That's a great question.
Problems that could actually be solved with clever, elegant math built directly into silicon. Keep that in mind the next time you hear about a massive new computer chip. Thanks for joining us on this deep dive.